Hello class. We're in lesson 4 of chapter 4 and we're going to learn about approximations today. We have a cartoon here at the very top of page 165 and let's read. You got the time? And the gentleman responds, about noon. Well, I'd prefer something more exact. And he says, about noon, stupid. Now, I certainly hope you would never call anyone stupid. Certainly not the right thing to do. But what happened was he was being more exact in addressing the person rather than more exact in the time. But let's go ahead and read on, and let's start at the top of the page. Ask someone to tell you what time it is, and he or she will probably give you an approximate answer. The answer may be to the nearest hour, such as about noon, to the nearest 5 or 10 minutes, such as about 12:05, to the nearest minute, such as 12:04, or even to the nearest second. In each case, the number that is the exact time is being approximated by another. So here we have a number line and we can see the 12, then we see the 12:04 and the 12:05, and the actual time was somewhere in between. Actually, time is always moving, so when you give an exact time, it's going to be a specific second, but you can even go into tenths of a second, hundredths of a second. If you watch the Olympics, you see how they time certain events by using these these watches or these clocks that are able to the hundredth of a second, and sometimes a winner or loser of an event could be just by 1/100th of a second. Okay, so imagine dividing 1 second into 100, and that was the difference between winning and losing. So they don't necessarily use approximations but it's still an approximation compared to 1/1000th of a second or 1/10,000th of a second. You can go further and further. So what would that look like? Well, we could say, let's say it's 45 seconds and then 16 hundredths. And then this would be the thousandths over here. Now this would obviously round up, and we'll, excuse me, we'll learn more about that. But we can go on and on and on and be more precise if we're actually capable of measuring with such precision. Scientifically today, we're able to measure things with an extreme amount of precision. Now, excuse me, let's go back to our text. The number that we use, the number that we use as a given approximation depends on the precision in which we're interested. For example, the rational number 22 over 7 written in decimal form is 3.142857 dot dot dot, meaning it goes on and on. All right. The first figure at the right shows that this number is closer to 3 than it is to 4. So let's look at the right, and we can see our number line, and we see that it's somewhere between 3 and 4. All right, and it's much closer to 3, obviously. Now, the second figure shows that it's closer to 3.1 than it is to 3.2. So we see that our second figure, 3.1, and it's somewhere close to the middle, but not quite exactly in the middle. Each successive approximation is more precise than the preceding one. If we go down to the next one, we'll see it 3.14 versus 3.15, and then the last one 3.142 versus 3.143. So we're looking to find exactly where within each of these number lines that are becoming much more precise. The number lines are changing in their units. In the first one we had whole numbers, then we had tenths, then we had thousandths, then we had 10,000ths. Okay, and if we continue reading, we will use the symbol. Okay, and then here's a new symbol. Goes like, oop, that's not a really good drawing. I can do much better than that. Okay, looks something like that, let's just say. Two wavy lines to indicate that an approximation is being used. The nearest integer of 22 over 7, the nearest integer is approximately 3. Okay, now to the nearest tenth, it would be 3.14. and so forth. So we can see how the symbol is being used. Let's turn over to page 166 and read on. In making an approximation of a given number, we generally have to choose between two numbers, one on the left and the other on the right. On the right of it on a number line. So we've already seen that. If a number is exactly midway between the two, one number is as good as an approximation as the other, right? So if it was right in the middle, in such cases, we will apply the following convention. We will choose the number that is farther from 0 on the line. And this is where we can talk about rounding up at 5, at 0.5, at whatever 5 shows up on our decimals, we can round that upward. So in this case, we had 1.25, right? So let's draw this number line here. Okay, and we're right in the middle, and we're seeing 1.25, which means this must be 1.2, and this must be 1.3. So 1.25 is exactly the same. It's equidistant. This is the exact, that's a 0.05, and this is also 0.05, okay? Now the question is, well, if I approximate, which way would I go? Well, we generally will round up or go further away. The 0 is over here. We're going to always go upward or closer or farthest away from the 0. And we'll explain why we say farther away from the 0, because we'll also do this negatively. So we would go farther from the 0, which means we would say if we were going to give this in tenths, 1.25, okay, is approximately, those are wiggly lines, not equal, is approximately 1.3, okay? So we're taking and we're rounding the 0.25 up to 1.3. Now if these were negative, it would actually be the other way around. Let's go ahead and draw the negative side. And here's negative 1.25. And if that were the case, then we know negative 1.2 would be on this side now, and negative 1.3 would be on this side. And again, we have the same distance, 0.05. Actually, it's a negative in a certain sense. If we took the whole, or excuse me, the absolute value, we know it would be 0.5, but we're going in this direction. Let's say there would be a 0.5, a negative 0.5. I'm just saying in relationship to 1.2. It technically is just 0.05 difference. But for the sake of working with the negative numbers, we'll just identify it as negative 0.5. 0.05 is what it should be here. I think I wrote that off over here as well. That's wrong. It should have been 0.05. So let's make that 0.05. Should be using zeros as well to note these things because you could lose your points. So it's good to have the number to the left of the decimal. So the difference between these two problems, the positive and the negative, is that we're now moving to the left away from the 0. The 0's over here, right? So we would round upward to negative 1.3. So we could say negative 1.25 is approximately negative 1.3. So in both cases, we're moving away from the 0 and we're rounding upward, okay? So let's read on. This means that to the nearest tenth, 1.25 is approximately 1.3, and negative 1.25 is approximately negative 1.3. Ordinarily, we would write a number such as 1.3. Excuse me. Ordinarily, when we write a number such as 1.3, we mean exactly 1.3. In approximate arithmetic, however, the quote 1.3 means 1.3 to the nearest tenth. The number written as 1.30 means 1.30 to the nearest hundredth. And we can see 1.300 means 1.300 to the nearest thousandth, and so forth. Okay, so we've learned here about approximations. Our precision is what's going to determine which decimal point we're going to approximate to. But we should understand, at least in the beginning, as we move away from the decimal point, we have the tenth, we have the hundredth, and we have the thousandth. But we can go further, the 10,000th, the 100,000th, the millionth. Okay, just put that th at the end, and you can go further and further and further. So that's the end of this lesson. You can go on to your exercises now.